today we are looking at our first topic for the day, at least, is going to be on homogeneous spaces and orbits. So our setup, we're going to let G be a Lie group, H a group submanifold, and we are going to form the left coset space of G over H. Then G over H is the quotient space of G, defined by the equivalence relation R, giving that x comma y are said to be equivalent if x inverse y is in H. And this gives us a theorem. R is a regular equivalence relation so that G over H has a unique manifold structure such that our injection from G to G over H as pi is a submersion. So if you recall from our definition of what makes an equivalence relation regular, giving us all that consequences, we need, first off, we need R to be a submanifold of G times G. And we want our second projection from R to G to be a submersion. For our first part, define the map P from G times G to G by P of x, y being x inverse y, which will of course make R just be the inverse image of H under P. And we know that it suffices to show that P is everywhere a submersion. So we're going to pick a pair of elements x, y in G times G. Oops, okay. And we're going to let a function phi from G to G times G be defined as sending an element to z to x comma x times z. And then phi of x inverse y. Well, our left element is always x, and our right is this times on the left by x, which will cancel out the x inverse, so we get that. So we get our xy. And we have that p acting on our phi is going to be the identity on G. So P is a submersion. So now we know that the second projection is a submersion. So now we consider the composition from G times H by phi to R by our second projection to G, where psi of x comma h is equal to xh comma x, for of course xh being inside G times H, which you can tell just by our composition diagrams are in the left. Then the second projection of psi is the projection on G which is a submersion. As psi is surjective, PR2 is a submersion. Alright. So now we have a couple of remarks from this. First off, we have the natural action of G on G over H is analytic, as we have a diagram that commutes G times G to G in a typical product. We can then, or we can alternatively project the right element onto G over H. And this thing is clearly going to commute. And the vertical maps are surjective submersions. And the top map is analytic. Now, I'm sorry, one second. Secondly, suppose H is a normal subgroup of G. Then G over H is a Lie group. By a diagram such as above. We just essentially draw it again, and we see that our multiplication is now analytic. So, let G be a Lie group, which I'm going to write here as an analytic group, to pair with the fact that X is going to be an analytic manifold. And phi be a map from G and X to X be a morphism. Then we see that G acts on X by phi if, first off if phi of E in X is X, of course for all X in X, and if phi of G of phi of H of X is phi of G times H on X for all G, H in G, and X in X. Now, suppose G acts on X by via phi. They use via instead of by because they're trying to be fancy or whatever. Then we will often use the notation where phi of G on X is just written as if multiplication, just like any sort of group action. And we introduce some additional notation here just to make things a bit easier. So for an element G in G, LG is going to be left multiplication in G by G, and MG is going to be left multiplication in X by G. And we have, of course, also for X in X. We'll need a new page here. I don't need my phone to work. Phi of X is going to be the multiplication setting G to X by, I'm calling it right multiplication by X is kind of weird, but you understand what's going on here. And it's worth noting that LG and MG are analytic isomorphisms, and that phi of X can be written so you multiply an element H, take an element H and G, multiply it on the left by G inverse, and then apply phi of X, and then multiply it on the left now by G. which gives us the following homogeneity principle. Which we're going to write as HP. Let P be a local property. Then phi x possesses P. If it possesses P at one point in G. So phi of x is an immersion or submersion or subimmersion if it is at just, we only need to show it is at one point. And also we're going to fix x naught in x. Let H be a set of elements H and G such that they stabilize our x naught in x. Be the stabilizer of x naught. And we're going to write phi naught as phi of x naught. Now, this brings us to this is our setup for our second theorem. Suppose our right multiplication by x naught is a subimmersion. Then, first off, H is a group submanifold of G. And secondly, the induced map phi bar naught of G over H to X is an immersion. Our first one is actually just by definition. Our proof for number 2, we're going to pick an element G in G. Then the kernel of Tg at phi naught is Tg of G of H. So T of pi of G on phi bar naught of 0 is injective. So phi bar naught is an immersion. This is and then there's a corollary. We're going to let phi from G1 to G2 be a homomorphism of analytic groups, which is a subimmersion. We're going to let K be its kernel. Then, first off, K is a normal group submanifold of G. Secondly, the induced group homomorphism, phi sending G over K into G2 is an immersion. I'm guessing these G2 are supposed to be G1 in this context. Brings us to another theorem. Suppose that K, a characteristic of K, is 0. Then phi naught is a subimmersion. Let's look at the proof. So we're going to let G naught in G such that the rank, we call it n, of T phi naught at G naught is maximal. Then the rank of T phi is n in a neighborhood U naught of G naught. We're now going to define a property of a point P and G, stating that there exists a neighborhood U of G such that the rank of T phi naught equals n in U. We notice that P of G is an local property and is true for G being G naught. By the homogeneity principle, PG is valid for all G and G. So phi naught has constant rank and is a subimmersion as character of K is 0. Oof. Alright, we got another theorem here. Suppose that G is locally compact and is a denumerable union of compact sets, and that phi of G being G of X naught is locally closed in X. Then okay, first off, we see that the induced map phi naught bar from G over H G times X naught is a homeomorphism. And secondly, if phi naught is a subimmersion, then Gx naught is a submanifold of X. And phi naught bar is an isomorphism of manifolds. And this is just by our previous lemma. This is automatic. And this comes with a nice handy corollary, which holds true in character 0. Gx naught is a submanifold of X if and only if Gx naught is locally closed in X. So we're now going to look at principal G bundles with the assumptions. First off, phi X is an injective immersion for all X and X. And secondly, given an analytic map phi from X to B, where B is an analytic manifold such that G of X is phi inverse of phi of X for all X in X. And that phi is surjective. We're going to let R be the equivalence relation on Y comma X for some reason. I'm going to be writing it in X times X such that there exists G in G such that Y can be written as Gx. So essentially, there's a element of G sending Y to X by action. Then R is of course an equivalence relation by properties of group. And our psi induces a bijection psi from X over R to B, which is going to be continuous. Now, I have a big set of assumptions it looks like. But in the system, consisting of our analytic manifold, our maps phi, our Lie group, and the psi and B from above, we call X, the total space, G as the fiber, and B as the base. And we sometimes write X for the entire system X, V, G, C, B. That brings us to another theorem. On X, the following are equivalent. First off, our map C is a submersion. Secondly, R is a regular equivalence relation. And C bar is an analytic isomorphism. Thirdly, for all B, there is a, for all B and B, I should write to make it a bit more organized, there is a neighborhood UB of B and B, and an analytic map CB sending UB to C inverse of UB such that C of sigma B is identity on UB. Number 4, for all B and B, there's a neighborhood UB of B and B, and an analytic map, analytic isomorphism actually in this case. Theta B from G and UB into C inverse of UB such that first off, we have a diagram that commutes from G and UB. We can send this by theta B, we know, isomorphically to C inverse of UB, which we can then send by C to UB. But we can also just send it directly there by our second projection. And our second condition here is that theta B of GH and A is G times theta B of H and A for all GH in G and A in UB. And our proof we've done 1 is equivalent to 2. We saw it as Gödel's theorem. We also, sorry, one sec, my hand is getting tired. So when applying 3, we saw a bunch of equivalent definitions of submersions, and this was just by one definition of submersion. If you want to go back and check, it was the 5th definition. The only real step here is 3 implies 4. So we're going to find theta of G to be the map. It should be a colon, not an equality sign, from an element of G and an element of U and B to C inverse UB by theta B of G and A being G times sigma of B of A. Then theta B is a bijective morphism meeting A and B of part 4, you can see. To show that theta B is an isomorphism, we show it is étal at all G and A in G times UB. Well, let's see this. We let X be theta B of G and A, BG times sigma B of A, and we're going to let sigma be mg, our left multiplication by G on sigma B, which is going to be G as a function on sigma B. Since C composed of sigma is a density on UB, that gives us C is a submersion at X. And we note that we also have that TA of sigma is injective, and Tx of x is the direct sum of the image of T alpha of phi and the kernel of Tx of C. Now, but since C inverse of A is G of X, and we have that C of X is an immersion, we see that the kernel of the tangent of X of C is Tx of G times X, which is going to be the image of the tangent at the identity of Cx. As the tangent at G comma A of theta B is Te phi x times d alpha sigma theta g is a tau at g comma a. And finally, we need 4 implying 1 is automatic. We're also done. We have a couple more little things, but they're both trivial. The definition. So suppose we have such a quintuplet x, v, g, c, b. X is then said to be a principal G bundle over our base B. Note that we consider the left action of G on X, giving a left principal bundle. We also have a right principal bundle. Brings us to another theorem, which is automatic, just being a special case of our previous theorem. Don't know why I'm underlining that. So let G be a Lie group with a group submanifold fold H. Let pi be the projection of G onto G over H. The projection, of course, of G onto the left coset space of H. And phi from G and H to G be multiplication. Then G is a right principal H bundle over our G over H. This is, of course, going to be our base. And with that, we will call it here. Next time, we're going to be looking at formal groups, probably for a little while. And then, yeah, then we're going to be moving on to Bourbaki, which is be a bit more exciting. I think we're going to have a bit of a appendix afterward here. I forget what this is called, but you know what I'm talking about. I always ramble at the end of these videos. I don't know why. Thanks for watching.